Hold out your hand. In that instant, trillions of invisible particles from the sun just passed through you, right through your bones, your DNA, and the entire planet as if nothing was there. These are neutrinos, the universe's best-kept secret. They're everywhere all the time, yet almost nothing at all. Ghosts in the cosmic machine. Why ghost particles? Because they're so elusive, so reluctant to interact that they make actual ghosts seem solid. Neutrinos have no electric charge, almost no mass, and barely interact with anything. They're the ultimate cosmic introverts, flitting through the universe, unnoticed. Yet, within their ghostly nature lies the key to some of the deepest mysteries of existence. Our quest to understand them is a cosmic detective story, with faint clues and a suspect that barely leaves a trace. To catch them, we've built extraordinary machines deep underground and even at the South Pole, seeking the faintest murmur from a passing neutrino. Every star, every supernova, every cosmic event sends out a flood of neutrinos, cosmic storytellers carrying tales from the hearts of stars and the dawn of time. If we can learn to listen, what secrets might they tell us? The story of the neutrino is the story of us, trying to see the invisible. These particles are not just cosmic curiosities, they're messengers from the universe's most hidden places. And if we can hear their subtle song, we might finally understand our place in the grand cosmic ballet. What is this phantom particle? In the early 20th century, physicists studying beta decay noticed missing energy, a cosmic crime scene. Wolfgang Pauli proposed a new invisible particle was carrying away the energy, the neutrino, the little neutral one. Neutrinos are fundamental particles, loners in the family of leptons, and unlike electrons, they don't feel the electromagnetic force. That's their superpower. They can fly through a light year of solid lead without hitting a single atom. They interact only through gravity and the weak nuclear force, both incredibly feeble. Where do they come from? Most streaming through you now were forged in the sun's core, a nuclear furnace fusing hydrogen into helium. This process unleashes a torrent of neutrinos, but they also come from supernovae, nuclear reactors, radioactive rocks, and even the Big Bang itself. Neutrinos are everywhere, from the most violent cosmic events to the rocks beneath our feet. They're relics of creation, still zipping across the cosmos after nearly 14 billion years. Despite their abundance, they're almost impossible to catch. Yet their existence is essential to the universe's story. They're the silent witnesses to the birth of stars and death of stars. And they may hold the key to understanding the universe itself. Imagine a cosmic rainstorm. Billions of neutrinos pass through your thumbnail every second. So why are they so hard to catch? Because to a neutrino, even a wall of lead is mostly empty space. With no electric charge, they glide through atoms, rarely interacting. The odds of a neutrino hitting an atom are astronomically small. You could live your whole life and never notice. Studying them isn't about better microscopes, it's about patience and probability. To catch one, you need two things: a huge number of neutrinos, the universe provides, and a massive detector with countless atoms as targets. Even then, only a tiny fraction will interact. But there's another problem: cosmic noise. Cosmic rays bombard Earth, creating a shower of particles that drown out the faint neutrino signal. It's like trying to hear a pin drop at a rock concert. To see a neutrino, you have to escape the noise. Hide from the universe to see its most elusive messenger. That's why neutrino detectors are built deep underground or under ice. Only then can we hope to catch a ghost. How do you trap a particle that can fly through the Earth? You use the Earth itself as a shield. Scientists build neutrino observatories deep underground or beneath Antarctic ice, using rock and ice to block out noisy cosmic rays. Only neutrinos can penetrate this deep, making it quiet enough to listen for their faint signature. The Super Kamiokande in Japan is a colossal tank filled with 50,000 tons of ultra-pure water, lined with over 11,000 light sensors. These sensors wait in darkness for the tiniest flicker of light, a sign a neutrino has interacted. When a neutrino strikes an atom, it can create a charged particle moving faster than light in water, producing a blue flash called Cherenkov radiation. This faint blue glow is the ghost's footprint. By recording which sensors saw the light and when, scientists can reconstruct the event, figuring out the neutrino's direction and energy. Every flash is a victory, a single neutrino caught after a journey of millions of miles. It's cosmic forensics at its finest. From a ghostly particle, we deduce the secrets of the universe. One of the first great neutrino mysteries began with our own sun. Scientists predicted a certain number of solar neutrinos, but when Ray Davis Jr. built the first major detector in a South Dakota mine, he found only a third of the expected number. His experiment, using a tank of cleaning fluid, was like searching for a few grains of sand on all the world's beaches. The missing neutrinos became known as the solar neutrino problem. For decades, other experiments confirmed the shortfall. Was our model of the sun wrong, or were the neutrinos changing on their journey? The mystery challenged the foundations of astrophysics and particle physics. Some thought the sun's core was cooler than believed. Others suspected experimental error. But a radical idea emerged. Maybe the neutrinos weren't missing, they were changing disguise. This puzzle would lead to a revolution in our understanding of both the sun and the neutrino. The answer would change physics forever. The sun's faint heartbeat was a clue to a deeper truth, and the hunt for that truth would reshape our view of the universe. The solution: neutrinos are cosmic shapeshifters. They come in 3 flavors: electron, muon, and tau neutrinos. Early detectors could only see electron neutrinos, the kind made in the sun. But neutrinos can oscillate, changing from one flavor to another as they travel. By the time they reach Earth, they're a mix of all 3, so detectors saw only a third. This oscillation means neutrinos must have mass, a direct challenge to the standard model of particle physics. The discovery, confirmed in 1998 by Super Kamiokande, was revolutionary. It solved the solar neutrino problem and proved our understanding of the sun was right. But it also opened the door to new physics, hinting at a deeper theory of the universe. The ghost particle, once a mathematical fix, became a guide to the unknown. Its secret life was finally revealed. On February 23, 1987, a massive star exploded in the Large Magellanic Cloud, a supernova called 1987A. Before its light reached Earth, a burst of neutrinos arrived first, heralds of the star's death. For the first time, we detected neutrinos from outside our solar system. Detectors in Japan and the US recorded a handful of faint signals, tiny flashes of light from particles that had traveled 168,000 years. The neutrinos arrived hours before the light, as expected. They escape instantly from the collapsing core, while light takes longer to fight through debris. These few particles confirmed our theories of stellar collapse. 99% of the explosion's energy is carried away by neutrinos. By studying their timing and energy, scientists learned about the neutrinos' mass and properties. This was the birth of neutrino astronomy. For centuries, we saw the universe only through light. Now we could peer into the heart of a dying star. The whispers from that supernova gave us a new sense to perceive the cosmos, and a new way to listen to the universe's most dramatic events. Neutrinos having mass might seem minor, but it connects them to the universe's biggest mysteries. The Big Bang should have created equal matter and antimatter, which would annihilate each other, yet we exist. Something tipped the scales, leaving a tiny surplus of matter. The answer might lie with neutrinos. If they are their own antiparticles, they could have helped create this imbalance. Proving this is a major goal of modern physics. Experiments are underway, searching for rare decays that would confirm neutrinos are their own antiparticles. There's more. 85% of the universe's matter is invisible dark matter. Neutrinos aren't massive enough to be all of it, but a heavier, sterile neutrino could be the missing piece. If these exist, they might be the dark matter holding galaxies together. The humble neutrino is a prime suspect in the universe's greatest mysteries. It could explain why we exist and what the universe is made of. The search for answers continues, and the neutrino remains at the heart of the cosmic puzzle. Our journey with the neutrino is just beginning. We know they have mass, but not how much or which flavor is heaviest. We don't know if they're their own antiparticles, or if there are hidden types waiting to be found. To answer these questions, new experiments are underway. The Deep Underground Neutrino Experiment will send a beam from Chicago to South Dakota, studying oscillations with unprecedented precision. In Antarctica, the IceCube Observatory uses a cubic kilometer of ice to catch high-energy neutrinos from cosmic events. Why do we hunt these ghosts? Because neutrinos are keys to the cosmos, probing places we can't reach any other way. Neutrino astronomy gives us a new sense, a way to see the universe in particles, not just light. The story began as a desperate fix for a missing law of physics and became a revolution in our understanding of reality. The hunt continues because as long as there are cosmic mysteries, we will keep listening for the whispers of the ghost particle. And in those whispers, we may find the answers to the universe itself.